All right, what I promised to talk about in the title of the lecture was the holographic principle. We've not talked about the holographic principle. The holographic principle is another extremely odd, but apparently really, what shall I say, a consequence, a logical consequence of what I've told you. So let me tell you what the holographic principle is. It again has to do with where information is really stored and how much information can be stored, but not for the moment in the vicinity of a black hole, but just in empty space. Let's suppose we have a region of space. There's a region of space. I chose it to be spherical for simplicity. It could be a very big region of space. It doesn't have to be small. It could be big enough to contain galaxies and planets and all that kind of stuff, but of some finite radius sphere. And the question is, what's the maximum amount of entropy that can be in there? The maximum amount of entropy that can be in a region is the maximum amount of information that can be hidden. It's also a measure of how many degrees of freedom it takes to describe that region of space. The maximum entropy of a system is, roughly speaking, how many distinct coordinates does it take to describe that system. All right, so there's our question. What's the maximum entropy can be here? It could be in the form of gas. It could be in the form of Swiss cheese. It could be in the form of people, whatever. How much hidden information can be, or how much information, period, can be inside, or how much entropy can be inside there. All right, so here's the thought experiment we're going to do. First of all, let's suppose that the entropy initially was S in. In stands for initial. The initial entropy is called S in. Now let's imagine that we have a large shell of material. We create a large shell of material out of whatever material we have available, interstellar gas, whatever it happens to be, and we arrange it in a shell, and then we project it inward so that it starts to fall in toward this region. Now let's choose the mass of the shell to be exactly right so that when it's combined with the mass in here, it's exactly enough mass to make a black hole of precisely the same radius. You have to trust me, that's possible. There's no ambiguity about it, and there's no controversy about it. It is possible to create such a shell which is just right to create a black hole of exactly that size. So the shell comes in, crosses the radius r, and leaves a black hole. What's the entropy of that black hole? The entropy of that black hole is the area of the region, just the same formula, times c cubed over h bar g. Most important is that it's the area in Planck units, 4 times that. It's the area in the units of this very, very small Planckian area. What does it say? First of all, the second law of thermodynamics says that the entropy after you do this must be bigger than the entropy before. Entropy increases. Therefore, we learn the following, that the initial entropy must have been less than or equal to, could not have been bigger than the area times this other stuff here. That's a limit. That's a limit on how much entropy could have been in that region of space to begin with. It didn't really depend on whether there was a black hole there or whether there was a shell of matter there. Even if the shell of matter wasn't there, just the fact that we could have created it and sent it in tells us that the entropy in a certain region of space cannot be bigger, can never be bigger than the area of that region in Planck units. That's really interesting because in all other physics, the maximum entropy of a region of space is proportional to the volume. It's also true in most other physics that the number of degrees of freedom that it takes to describe a region of space is proportional to its volume. We have found out by the series of indirect arguments that any region of space can be described by a collection of degrees of freedom which are no more numerous than the area of the region in Planck units. That led to a conjecture. It led to a conjecture that any region of space can be described by some kind of theory describing degrees of freedom on the boundary of the region of space. That is what was called the holographic principle. Holographic because it's like a hologram. That was a conjecture. It was a, you might even call it a speculation, which is worse than a conjecture. But it was in 1994 or so that this conjecture was put forward. Most people at the time thought it was a screwball notion. But it took a couple of years, basically until 1998, until a young Argentinian physicist whose name you should know. I ask people, do you know who Juan Maldacena is? I'm talking about physicists or physics groupies and so forth, and often they don't. Juan Maldacena is perhaps the greatest physicist of his generation. Juan Maldacena produced a perfectly rigorous description of this for a particular kind of space-time called anti-de Sitter space, but that's not what's important. What's important is he dotted the I's, crossed the T's, and found an extremely precise mathematical description of the degrees of freedom on the boundary which would describe a region of space. And indeed, it turned out that there were no more of them than one per Planck area on the region of space. So in some sense, the world is really described by a kind of holographic description on its own surface. Just to make it graphic, everything in this room, there is enough degrees of freedom on the walls of the room to describe everything in the room. It is as if the walls of the room could be thought of as a hologram describing what's happening in the interior. Okay, so we got through the holographic principle. Thank you.